the first example here on page 5, a city council commissioned a statistician to estimate the proportion P of voters in favor of a proposal to build a new library. The statistician obtained a random sample of 200 voters with 112 indicating approval of the proposal. We want the point estimate for P and the 95% confidence interval estimate of the population proportion P. Right, so the point estimate that's your sample proportion. Which we abbreviate with a P hat. All right, so we worked with Y hat last unit, now it's P hat. All right, so now that P hat is equivalent to the number of successes over the number of trials. All right. So in this case, and we learned with binomial probability, well, actually any kind of probability, that success is in the eye of the beholder. Like, if we're talking about a life insurance policy, the success would be cashing out that policy, but that only happens if you die. So it's not really going to feel very successful, right? In this case, we're talking about 112 individuals indicating approval. So here, success really is success, right? So they're approving, unless approving this proposal is considered to be a bad thing, but I don't see how that would be the case here. Right. Actually, I shouldn't even say that. To be fair, some people just vote no because they don't want their taxes to go up, right? Regardless of how awesome that new library is going to be, you know. So the renovations that they're doing around here, they put it to a vote. Like, there are people that say, "You said yes, that's terrible. Now our taxes are going to go up." Right. So yeah, you just got to be careful about the perspective, and that's really it. Right. So the point estimate is now determined to be 112 over 200. You can put it in decimal form if you want. I recommend not doing that. Right. Because the calculator, I'll show you the calculator shortcut in a minute. The calculator is set up to accept whole number values for this type of confidence interval. Now the formula for confidence, and this is something that you get on the AP formula sheet. Right, so, but they give it to you in little pieces. You just have to know how to put it together. So, P hat plus or minus Z alpha divided by 2 times the square root of PQ over N. All right. Or P hat plus or minus Z alpha over 2 times the square root of P hat Q hat over N. Yeah, it's a Greek letter alpha. Bless you. All right. You're going to have to decide whether to use the first formula or the second formula. Right? The first formula, and there's only subtle difference between the two, so kind of go either way. But you would use the first one if you can reasonably assume the population proportion P. All right, so that's when you would use this formula. I would say, I don't want to say most of the time, but very frequently, we're not going to be able to make that assumption. It's kind of like if we're estimating the proportion P, like, it is possible that we go into the problem having no idea, no sense of what it's actually going to be. All right. So a quick example would be if you had an election between two individuals. Now, I guess you can assume that there's a 50-50 chance, but one of them's going to win the election. So you got to figure the population proportion would be more than 0.5 for one of those individuals, right? But would it be 0.55? Would it be 0.75? Would it be 100% of the population? I doubt it, but you never know. Right? If you somehow get your opponent to vote against themselves, that's entirely possible, I guess.
What's the circumstance where you could assume that?
They'll give it to you in the problem. They'll say historically the winner of the election has won at a rate of 0.6. So I kind of look at the first one as being a little bit more academic, the second one being a little bit more practical. All right. So if we come up with the computations here, then we're in good shape. Then we'll have our confidence interval. Right? When they say 95% confidence, so the confidence level, so the C level, is 95%. Alpha is equal to 1 minus the decimal form of that. So this is 0.95. So it's 1 minus the confidence level in decimal form. So 1 minus 0.05. Up, getting ahead of myself, sorry. 1 minus 0.95 is 0.05. All right, so we have our alpha value. Now what we need is the z-score corresponding with alpha over 2. All right, so alpha over 2, no surprise there, that's just going to be alpha over 2. So 0.05 over 2 should end up in most cases, in all cases that we're going to deal with, some nice values there. Right? But the z-score corresponding with that could be pretty hideous. Now, what's happening here is that alpha is representing a certain amount of area under the normal curve, but specifically on the fringes. So when I talk about 0.05, 0.025, whatever, what we're doing is we're saying if we want 95% confidence, we want an interval of value that contains 95% of the data. All right, which leaves 5% for the fringes. All right, so this actually ties together with usual and unusual values. This is actually the process that we would use. All right, but we're looking at it from the perspective of the tails. All right, these two tails have to add up to 0.05, but it's symmetric, which means that this one would have to be 0.025. Same deal over here. All right, so what I want to determine is what these values are. All right, so we go back to our first half of the unit in probability, I believe. Even before that, we covered it in Unit 1 also. But I'm going to go into my calculation menu, toolbox, and under probability, we're going to select distributions, normal, things. It's inverse norm. So inverse norm. And because we're working with a standard normal distribution, you could really just put in the 0.025, 0, 1, and not really worry about anything else, right? Because we wouldn't have the mean and standard deviation for this distribution, because we don't have. Well, I suppose we could use the binomial formulas, but then we'd have to go down the list and say, is there a fixed number of trials, fixed probability, independent events, and 2 outcomes, right? But this kind of avoids having to deal with that, so just 0 and 1 is all you need. So 0.025, 0, 1. So yeah, negative 1.96. All right, so since it's symmetric, negative 1 like we're actually rounding it to negative 1.96, even though we want to go 3 significant digits. That's just how it works out. So negative 1.96. Since it is symmetrical, the other one has to be positive 1.96. So I now know my z alpha over 2. The plus minus actually just comes from the sign of those z-scores, right? One's negative, one's positive. So it just kind of naturally works its way into the formula. All right, so we'll use this formula here because I don't know what the historical approval rate is. It's possible that it's like just a smidge over 0.5 or 0.75. I have no idea, so I can't make a reasonable assumption about the population proportion P. So I'm going to use this variation of the formula. So p hat 112 over 200 plus or minus 1.96 times the square root of p hat q hat over n. Now the q and p are related in that they're complements of one another. So q hat, oh, that looks terrible. Q hat is equal to 1 minus p hat. That's like a quick FYI. Right, so 112 over 200. And you could do 1 minus 112 over 200, but computationally it's not awful to just subtract 112 from 200. So 88 over 200. And we run these numbers, right in the home screen is fine. 112 divided by 200. I'll do the minus first, 1.96. And for a little bit more accuracy, you can just use the previous answer. You know, just hit answer. But when I go to do it again, it's yeah, Q hat. All right, so, but I'm just gonna retype the elongated decimal, I guess. All right, so times the square root of 112 over 200 times 88 over 200 divided by just another 200. So I'm writing it like that so I could just do, bless you, so I could just do a copy and change the minus to a plus. But we're looking at an interval going from 0.491, and now I'm just going to replicate it. To 0.629. All right. Now every confidence interval comes with a conclusion statement. Well, meaning you have to write the conclusion statement. So, and it's always structured the same way. We are 95% confident that the population proportion of voters that approved the proposal, something to talk about what the statement is in relation to, voters that approved the proposal is between these two numbers, 0.491. Right? It's a proportion, so you don't need units. You know, if you wanted to, you could say 49.1%, but I totally understand if you don't want to do that. And 0.629. Right? Now, like I said before, we'll get into the why down the line, but we can address at least part of this conclusion and what it means. And that is, if we're looking at like 0.5, let's say the population proportion was 0.5, that would be the boundary between a minority or a majority. So if I tell you that I'm 95% confident that 50% of the population is going to vote for this proposal, I'm not really telling you anything, because that means 50% is not going to vote for it. Right? So it's 50-50, it could go either way. Right? If I tell you that I'm 95% confident that 60% is going to vote for the proposal, what I'm saying is I'm 95% confident that the proposal is going to pass. Right? Because 60% is a majority, simple majority. Right? If I tell you I'm 95% confident that 40% of the population is going to vote for the proposal, I'm saying I'm 95% confident that the proposal is not going to pass. Right? Because 0.5 falls in this interval, it's just as plausible as any other value in that interval. Right? So I can't reasonably conclude that the vote is gonna pass because 0.5 is in here, and 0.5 is the 50-50, could go either way. If both parts of the interval were above 0.5, that would be an indication of a majority. If both parts of the interval are below 0.5, then it would be a simple minority, right? So, just very quickly, I'll just do it off on the side here. So, 0.5, that's kind of the balance point between the two. If the entire interval is to the right of 0.5, that's a majority. If the entire interval is to the left, that's a minority. If it straddles the balance point, then that's no conclusion, right? Or inconclusive. Right? So, I mean, you could just remember that if you want, but if you really think it through, it just makes sense.
So if your interval is like 0.3 to 0.5, would you still say inconclusive? Just because 0.5 is in it?
Yes.
Okay.
All right, the second example, it'll go quicker because things are usually easier the second time around. The thing that people, I'll tell you, just kind of flashing forward a couple weeks, looking back on this, if you're gonna struggle with this, it's most likely gonna have to do with the conclusion writing, because the calculator's gonna do most of the work for you, right? So, so we'll just have to work on that. But if you take the conclusion writing part of it seriously, then this is not going to be a challenge whatsoever. All right. Same thing with hypothesis tests, which is what we're moving into, and it's kind of weird because like this part of the course, this unit is really the culmination of everything that we've talked about before, but it's actually one of the quicker units because we talked about all that other stuff so much over time. I mean, you think about it, 3 marking periods roughly, like 2.5 marking periods we spent on the first 3 units. Like we did one kind of like a self-study sort of thing, but this last one is going to be pretty much half a marking period done, you know, because everything that came before it brought us to this. Okay, the only difference between this problem and the one that we just did is that our confidence level is changing. Right. So same structure. What's the point estimate for P? We know that. So P hat. Oh, that's not a marker. 112 over 200. We want 90 and 99% confidence interval estimates. All right. So if we look at our formula, the P hat plus or minus all that stuff, I'm still going to have a 112 over 200 plus or minus. The Z alpha over 2 is going to vary, but I'm still going to have the other part of it, the 112 over 200 times 88 over 200. Well, and then divided by 200, but yeah, those are the important parts. All right, so for a 90% confidence interval, CI for confidence interval, the alpha value is going to be 0.10, because again, the 90% goes to decimal form, 0.9, subtracted from 1, that gets you your alpha. Alpha over 2 is going to be 0.05. For 99%, the alpha value is 0.01, making alpha over 2 0.005. Right. So what I'm going to do is I'm going to recycle this, but instead of putting in a particular decimal value, I'm gonna put in the inverse norm right here. So in my toolbox, inverse norm, and I'm gonna use a dummy value. I'll just call it A. You don't have to do it exactly like this. You do it any way that makes sense to you. But I'm gonna do it this way so that I can store values in for A. All right. So I have my formula set up. I need to do this multiple times, so you know it makes sense to use something that is a little bit more general. All right. So it says undefined because I haven't defined A. But what I can do is I could take. I'll just do the previous example, the 0.025. I'll store that in right above the x to the y power key, this key here. if you hit shift and then that key, it brings in the arrow. So now anytime I hit A, oops, that's not an A. Now it's EA. At least we're in the game. Right? So A is now valued at 0.025. So when I run this computation, it gives me the high bound that we came up with earlier. High bound. That should be low. Oh, because the negative, the 1.96 is actually negative when you run this computation. So it'll give it to you in reverse, which is fine, I guess. But for this one, I want a 0.05. So I'm going to store that in. Oops. Shift. Oh, jeez. The whole fat finger thing is what's getting me. Shift. It's not like registering that I'm hitting shift. Yeah, all right. Well, that sinks. It'll work perfectly fine on your handhelds, but for me, I'm just gonna do it this way. Oh, now shift works. Oh, great. Oh, boy. Nope. It's giving me a hard time here. Let me. .05. On the low bound, we're going to get a 0.502. So the CI, confidence interval, is going to be 0.502. And then I'll do it again with a minus 0.617. 618. A little stray mark here. And then just do it again, this time with 0.005. So this is going to give me my high bound. And again, it's the minus is given the high bound, the plus is given a low bound, and that's again because when we do inverse norm, it gives us a negative number. So 0.4, it'd be 0.470. All right. So as we increase, just in comparison to the previous confidence interval where we had 0.491 to 0.629, as we increase the confidence level, it expands the interval. All right. So the lower bound is lower, the higher bound is higher. As we decrease the confidence level, it narrows out the interval itself. The example I always give for this is it's like if you had to guess my age, which are you going to be more confident about? If I tell you my age is between 41 and 44, or if I tell you my age is between 15 and 99. Like 15 and 99, it gives you more area to get it wrong.